Hello again, everybody. Today we're going to be talking about the analysis of variance, or we sometimes shorten up to simply say the Anova, A-N-O-V-A. With the Anova, what we're talking about is, again, we're still in that same topic of means comparisons like we are when we talk about things like the t-test, the dependent or independent samples t-test. But what makes the Anova different is that instead of having a requirement of two categories, we can actually have multiple categories, more than two. Now, by the way, SPSS will allow us to run an Anova with only two categories, but ultimately your results are going to look very similar to that of a t-test, so there's really no need. And in fact, in some ways, the t-test is a little bit easier to use since part of its standard output is going to be looking at the test of the inequality of variances. And you'll see that with the Anova, this is actually something extra we'd have to add on. And in fact, with the Anova, there's a lot of extra we have to add on. But before we get going, one thing I do want to remind you is that the analysis of variance is a hypothesis test that one of the means is statistically significantly different than the other. It doesn't mean that all of the groups have to be different from one another. So for example, if we have a low, a medium, and a high group, chances are good that we might see a difference between, say, like the low and the high, even though we may not see a difference between the low and the low and the middle, and the middle and the high. So always remember that we're only talking about the difference between at least one of the groups. And that means that when we phrase our hypothesis, often in terms of the general Anova, we have to take that into mind. Now, we're also going to talk today about the idea of the post hoc tests, which allow us to get into a little bit more detail. And we'll get to that after we talk about the Anova. So, in order to run an Anova, we need to identify two variables. One is going to be our dependent continuous variable, and once again, we're using the 2014 subset of the General Social Survey data. And so the only continuous variable here we have is age, and we need a categorical variable that has at least three categories. And yes, I know, again, I said before it could have two, but let's do the Anova for what it's worth. Let's go with three. So actually, I'm going to look at two variables today. Let's look at the variable of race, which we know has three categories, and then we'll look at the variable of marital status, which I believe has six. So in order to run an Anova in SPSS, we're going to go to Analyze. And like I said to you before, we're still comparing means, except the difference now is we're calculating the means within each of the separate groups, in this case, three groups. And what we're really getting at is looking at the difference in what we refer to as the sum of squares. In essence, the variation within versus the variation between the groups. So if we go down to compare means, you're going to see that the very last option here is called the one-way Anova. And we're going to click on that. Now you get two variables that you can select here, two types of variables you can select. The dependent variable, which obviously is pretty straightforward. In this case, we know that's going to be the measure of age. And then what they call the factor variable. And this is going to be our variable with our categories. Now again, like I said, we could do something like sex, but let's go with race because again, we're going to really highlight the benefit of using this as compared to a t-test, which only allows us to look at two groups. We can actually look at all three. Now, I'm going to purposefully do this. I'm going to just simply click OK here, and you're going to see that we get some information, but not very much. And you might notice on the right-hand side, we have a lot more options than we did, for example, with our t-test. And there's a reason for that. But for the moment, let's just click OK and see what we get. And you can see that the output we get for something like this is actually, it's pretty little. I mean, there's not very much information here. But ultimately, it is the hypothesis test. With our research hypothesis, for example, when we're talking about the relationship between race and age, our research hypothesis would be that our groups are different in terms of their average age. Our null hypothesis is that they're not different, or not statistically significantly different. Here you can see we end up with an F-test statistic of 30, which far exceeds our critical value, and that's reflected by the fact that our sig value is actually listed as 0.000. Now, you should all know by now, of course, that there's really no such thing as a sig of 0.00, and instead, that this value of 0.000 is actually reflecting the value of 1.28 to the e to the negative 13th, which means that we should move the decimal place 13 spaces to the left. In other words, the probability of this event occurring by random chance is incredibly small. Now, as I talked to you before about the idea of the variance, you can see that the sum of squares as well as the mean squares are being calculated out here. And just for your own information, the sum of squares divided by the degrees of freedom gives you the mean square, and then the mean square between divided by the mean square within is actually how we get the F statistic. Probably more information than you care about necessarily in terms of your SPSS output. But ultimately, giving us this sig value, which is very, very small. So this allows us to draw the conclusion that at least one of the groups is statistically significantly different from the other. The problem is we still don't have much information here. So here's what I'm going to do. I'm going to go to Analyze again, back to Compare Means in my one-way ANOVA. Now I'm going to leave the setup here the same with the age and the race. But what I'm going to actually do is I'm going to go over here where it says Options, and you can see that one of the options right away is descriptive. And let's select that. Once we do that, let's say Continue, and then OK. And now we get a little bit of information here that can actually help us understand what's going on. Because now we get some differences here in the average ages by the groups. So you can see here that the average age for the white respondents is about 50, about 45 for the black, and then about 40 for the other. So right away, and this is the example we were using before, it could very well be the case that there's no statistically significant difference between white and black. It's only about 4 or 5 years. Might not be a statistically significant difference between black and other. It's only about 4 years. But there has to be a statistically significant difference between white and other. I mean, that's an enormous jump. It's almost 10 points there, a little over 9 points. Now, again, the problem is I'm eyeballing this, and that's not a very smart way for me to handle this. So we have one other option we can do, which is going to be referred to as a post hoc test. Now, the ANOVA has told us that there is a statistically significant difference between at least two of the groups. It just hasn't told us which groups are different from one another. So let's go back to Analyze one more time. I'm going to go to Compare Means. I'm going to go to ANOVA. And this time, let's click over here where it says Post Hoc. And I'm actually going to select the Tukey statistic. And I'm going to say Continue, and then OK. And what you can see is as we scroll down here, the main thing of interest is this section here with the post hoc tests. You can actually see that what the program has done is provided a statistical breakdown looking at whether or not the mean differences between each of the groups is statistically significant. So for this case, you can say for our white respondents, how different are they from the black and how different are they from the other? And you can see on the average, the age difference between white and black respondents is about 5 years. And for the other, it's about 9 years. And again, part of this is repeated here for black to white, 5 years being repeated again, what black to other, about 4 years, and so on down the line. The main thing that's interesting here is if you take a look at the sig values, all of these fall below that 0.05 cutoff. Now, what's interesting is notice that black to other and other to black, it is statistically significant, but it's almost not, right? It's pretty close as compared to the others to that 0.005, which makes sense because the difference there was only about 4 years in age as compared to 5 or 9 with the other groups. But what the benefit of using something like this is, so we reject the idea that the means of the three groups are different, and now we can go a step further and actually look at how these means differ from one another. All right? Ultimately, this is a benefit of using an ANOVA. So let me take a look at one more. And this time, I'm going to go to Compare Means, ANOVA. I still have to leave age in here because it's my only continuous measure in this data. I'm going to take that out, and instead, let's put in marital status. And now, remember, it saved all my commands from last time, which means that the descriptive and the Tukeys are both going to come up as part of the output. And I'm going to say OK. And you can see here right away, clearly there's a statistically significant difference. Our F statistic is equal to 300. Our sig value ends up being 1.36 to the negative 205th. So move the decimal place 205 to the left-hand side. Now come over here and look at this, and you'd say, well, of course there has to be a statistically significant difference. Average age of married is 33. Average age of widowed is about 73. The differences here are enormous. And in part, I did this a little bit purposefully. This is a variable which is really actually rather dependent on the idea of age, isn't it? People are much more likely to never have been married when they're younger, and they're much more likely to be widowed when they're older. At the same time, we'd expect people who are divorced are going to be older than people who are married. So the idea here is that, yes, there is a very strong, significant relationship because at least two of these groups are statistically significantly different from one another. And if we scroll down here, you can see that for the most part, most of them are different from one another. Now, the only exception is notice here that married and separated, it is not a statistically significant difference, but all of the others are. Again, two-step process here between running this, running the Anova, and running the post-hoc test allows us to both test the general hypothesis that the groups are different from one another, and then the post-hoc tells us where the differences are. Now, if I was only interested in a couple of the groups, maybe the married versus the never married, or the widowed versus the divorced, or whatever it is I'm interested in, then I could have just used a t-test. I wouldn't have needed to use the Anova. But assuming that I've got 3 or more groups, all of which I want to compare, this is a smart way for me to handle it. All right, that's about everything I really wanted to cover here in our discussion of the Anova. So, as always, I wish you all have a very pleasant day, and feel free to contact me if you have any questions. Take care.